Welcome to my tutorial on balancing equations. Today's learning objective is to be able to balance symbol equations. Now this lesson is actually going to be split into two separate tutorials. Lesson 1 is the background knowledge required for balancing equations. Lesson 2 is my tally method for balancing equations. Now I would recommend that you have a break between these two lessons because they're quite heavy going. It's really important that you get lesson 1 out of the way to ensure that your subject knowledge is strong enough to attempt to balance an equation. So lesson 1, this is a background knowledge required. You need to be secure in your understanding of the following. So what actually is an atom and a molecule? What do we mean by elements and compounds? What's an ion? And what are formula? Or formulae, plural. We are going to recap on the above before learning to balance equations. So atoms, molecules, elements and compounds. What is an atom? Well, the atom is the smallest particle of an element. An atom is made of subatomic particles itself called protons, electrons and neutrons. But without the whole package, we can't call it an element. So for example, if we look at this diagram here, of a lithium atom, that's the most simplest form of lithium. You can see that lithium, its atoms contain 3 protons, which are positive within its nucleus, 3 neutral neutrons within the nucleus, and then it has 3 electrons, 2 in its first shell and 1 in its outer shell, so 3 in total. You can see what makes that particular atom lithium is the fact that it's got 3 protons. That is specific to lithium. So an atom is basically the smallest particle of an element. An element is a substance made up of atoms that all have the same number of protons in their nucleus. So just like lithium had 3 protons in its nucleus, hydrogen is an atom with 1 proton in its nucleus, and helium is an atom with 2 protons in its nucleus. Now, for the sake of this tutorial today, I would like you to represent an atom as follows. We're going to simplify it because today is about balancing equations. So we will go into the structure of atoms in another tutorial. So a molecule is made of 2 or more atoms chemically bonded. So some non-metal elements exist as molecules made up of 2 atoms joined together. So for example, oxygen is O2 and chlorine is Cl2. That subscript or small 2 literally means that you've got 2 oxygens joined together. Similarly, here you can see the 2 here means you've got 2 chlorines joined together. So that would be represented as follows: O2, Cl2. Compounds are always molecules. And this makes sense because what are compounds? They are basically 2 or more different elements chemically bonded. So 2 hydrogen atoms, that's 1 element, bonded to 1 oxygen atom, which is your second type of element there. So although you've got 3 atoms there, you've actually got 2 different types of element. You've got hydrogen element, you've got oxygen element, but you've actually got 3 atoms in total there, but of 2 different types. So compounds are formed when elements react. The atoms of each element are in fixed proportion throughout the compound. So water is characterized by the fact that it will always have 2 hydrogens and it will have 1 oxygen atom held by chemical bonds. If you introduced another oxygen to this molecule, that wouldn't be water anymore. That would actually be hydrogen peroxide, which is what you would use to bleach your hair. You wouldn't want to drink that. So what's a mixture? Well, if we look at the molecules on the page here, that's a mixture. You've got 1 element of oxygen. You've got another element here, which is chlorine. And then you have a compound here of water. If you put them together, you have a mixture of 2 different elements and 1 compound. Mixtures can be just of different elements, or mixtures can be of different compounds, or mixtures could be elements with compounds, as the example that we have here. So I want you to take a break now to have a go at answering A to H. So I'd like you to pause your computer, pause the tutorial, and see if you can label each of the following as an element, compound, or mixture. You'll need some paper. So if you write A to H down on your paper and then decide if it's an element, or compound, or a mixture, and be able to justify your decision. Pausing your video now. Right, I hope you paused that video to give yourself opportunity to answer those particular questions. What we're going to do is we're going to go through the answers now. So if you look at A is an element. And I'm hoping that you would have been able to justify that, because you can see you have only one type of atom there. You can see it's one type of atom because the particles that I've drawn, okay, the atoms, are the same size and the same colour to represent that they are of the same type. Again, B is an element too. Again, you've only got one type of atom here. Now, if you could compare these two elements, that could be oxygen, which goes around in pairs, O2, oxygen, oxygen. They're covalently bonded because oxygen goes around in pairs. Something like this could be a noble gas, for example, helium. Helium goes around as single atoms. Right, C is a compound. So that could be water, okay, or water vapour. You can see that you've got two hydrogens and you've got an oxygen there, for example. Now we know that's a compound, and the reason why we know it's a compound is because there's more than one type of atom. I hope you notice that the atoms that I've drawn here are different sizes, and that would suggest that they're different atoms. An examiner would most likely show different shading to show that they're different atoms, black, grey, white, might even put different patterns, or they will show the atoms as different sizes to represent that they are different elements. So that is your compound. You've got two of one type, one of another type of atom, chemically bonded. D is a bit more simple. D is actually a compound too, because you've got two different elements, so two different atoms chemically bonded together. Same for E. Now F, you have two different elements in there, two different types of atom, but because they're not chemically bonded, this is one element, that's a different element. So that's actually a mixture of two elements. G, again, is a mixture, but this time you have a mixture of compounds. That's one type of compound, it's the same one you have here, and there's a different type of compound in here as well. So you've got two molecules of that compound on one molecule of that compound. That is a mixture. And then H, again, is an element because you only have one type of atom present. I hope you managed to get 100% on that task. Right, so now we're going to look at ions. So we're going to look at ions, we're going to look at ionic bonding in a further tutorial. But for now, I'd like you to understand the concept that an ion is just an atom, like the ones we've come across before, or a group of atoms that's lost or gained electrons. Now, as we know, electrons have got negative charge. So if they have gained electrons, they become positive. If they've lost electrons, they become positive. So losing negative electrons gives it a positive charge. Gaining negative electrons gives it a negative charge. So in an ion, the number of protons doesn't equal the number of electrons. And that's really important because in an atom it does. The positive protons cancel out the charge of the negative electrons. But in an ion, this doesn't happen. Because you've either got too many or too few electrons, you have an overall charge. So for example, an ion with a 2 negative charge has 2 more negative electrons than positive protons. So if we look at this example here of sodium, Sodium's in group 1. This shows a sodium atom. That particular sodium atom there has 11 negative electrons. You can see 2 in the first shell, 8 in the next shell, and you've got 1 in the outermost shell. That's 11 in total. Within the nucleus of sodium, you would have 11 positive protons. So its negative electrons are cancelled out by those positive protons, and vice versa. If that sodium was to lose an outer electron, so it loses that electron, you can see now that sodium only has 10 negative electrons. And because it only has 10 negative electrons, that means that because it's got 11 positive protons in its nucleus, it has an overall charge of 1 plus. We don't write a 1, we just leave it as a plus, but that means it's 1 plus, positive by 1. Now, these ions you should really know. These are the positive ions. In the tutorial later, I will actually provide you with these ions, but it's really important that you actually take some time to learn these off by heart. It will speed you up in the exam. Some of them you can work out, but if you can learn these off by heart, again, it will give you a real advantage in your exam. So if we look at these, all metals will give you positive ions. And the reason why that is because they lose electrons from their outer shell to gain a full outer shell. We'll learn a lot more about these when we do ionic bonding. So group 1 lose 1 electron from their outer shell to form 1 plus ions. Group 2 lose 2 electrons from their outer shell to form 2 positive ions. Transition metals can actually have more than 1 ion with different charges. Now, for example, if I took something like copper, for example, copper sometimes is written like this with Roman numerals in brackets, or even like this with the symbol with the Roman numerals. Now, what that means is that's a copper 2 plus ion. That's copper 2 plus, okay? So you can see that's a 2 plus ion. If that had Roman numeral 1, it'd be copper plus or copper 1 plus. So with transition metals that actually have more than 1 ion with different charges, they will show those different charges in brackets, okay? Not always, but a lot of the time, especially in exam. So if we look at the negative ions, how you can remember that non-metals form negative ions is a little bit of alliteration. If you think N for non-metals and N for negative ions. Why they're negative is because non-metals actually gain electrons to their outer shell. So a group 6 requires 2 more electrons to its outer shell to have a full outer shell, so it forms a 2 negative ion. Group 7 just requires 1 additional electron for its outer shell to get a full outer shell. So it's a 1 minus ion. And then you can also see that you've got some molecular ions here as well. A molecular ion is a charged particle containing more than 1 atom. It's really important that you learn these. So if we come back to compounds again, we've just learned that the chemical bonds in a compound involve taking, giving away, or sharing electrons. Only the electrons are involved in a chemical bond. Nothing in the nucleus is changed. So a compound which is formed from non-metals consists of molecules. So each atom would share an electron or electrons with another atom. This is called covalent bonding. Now, there is another tutorial that I'm going to be uploading on covalent bonding. Look out for that. We're not going to go into it in any depth today, because remember, today is all about balancing equations. And this is just a bit of prior knowledge that you need to go forward with balancing equations. So for example, water, hydrogen chloride gas, and carbon monoxide all involve covalent bonding. They are all compounds. If we look at covalent bonding in water, you can see that that hydrogen atom shares 1 electron with that oxygen atom. That oxygen atom also shares 1 electron with that hydrogen atom. The crosses represent the electrons from hydrogen here, and the dots represent the electrons coming from the oxygen. So more on compounds then. A compound which is formed from a metal and non-metal consists of ions. We've just looked at ions on the earlier slides. So metal atoms will actually lose electrons to form positive ions, as we know. Non-metals gain electrons to form negative ions. And the opposite charges, those positive and negative ions, are actually strongly attracted to each other. And we call this ionic bonding. So for example, calcium oxide, you've got calcium ions attracted to oxide ions. You've got magnesium oxide, magnesium ions attracted to oxide ions. Oxide means oxygen. And sodium ions are attracted to chloride ions. Again, with the group 7, we replace the N in chlorine, iodine, bromine, etc. with a D. Similar here to what we've done with oxygen, where we've got the D here. Oxide, that means oxygen. Chloride means chlorine. So if we look at that example of sodium chloride there, you can see that sodium atom provides chlorine with the outer electron it requires to get a full outer shell. And by doing that, it has a full outer shell itself, but becomes a positive ion. Chlorine gains that negative electron to its outer shell and becomes a negative ion. And because these charges balance, you've got one positive, one negative, sodium chloride will attract each other strongly in a 1-to-1 ratio. So for every one sodium ion, you will have one chloride ion. So this leads us on to formulae. Okay, formula is singular, formulae is plural. So a chemical formula is used to represent an element or a compound in a balanced chemical equation. So for the formulae, in most cases for elements, is just its chemical symbol. So for example, Na from the periodic table is for sodium. So sometimes, okay, elements will go in pairs. So for example, if we take some non-metal elements that exist as molecules, for example, iodine or chlorine or bromine or oxygen or hydrogen, we know that all of those particular elements actually go around in pairs. And to show that it's going around in pairs, we actually give a subscripted 2 after the symbol. So for example, here you have iodine. Iodine is I2. That means you've got 2 iodine molecules that are covalently bonded. In a compound, the formulae gives the element symbols with subscripted numbers to show the proportion of one element to the other in a compound. So, for example, if we take water as our example here, you can see that subscript 2 means that you've got 2 hydrogens. But because there isn't a subscript number by oxygen, it means you've only got 1 oxygen. For that reason, water is made of 2 hydrogen atoms and 1 oxygen atom bonded together, chemically bonded. So if we look at formula in a bit more detail, so if we took sulfuric acid as an example there, you can see immediately you've got subscript 2, which would suggest you have 2 hydrogens. You don't have a subscript number after sulfur, so you only got 1 sulfur. But because you have a subscript 4 after the oxygen, that means it contains 4 oxygen atoms. So sometimes we have brackets in a formula. So for example, if we took magnesium hydroxide, you can see you've got Mg, open brackets, OH, close brackets, 2. That subscript 2 there means that anything within those brackets is multiplied by 2. That means you have 2 oxygens, but you also have 2 hydrogens. That 2 does not influence that magnesium. So, for example, in magnesium hydroxide, then you have 1 magnesium atom, 2 oxygen atoms, and 2 hydrogen atoms. If you were to see a coefficient, which is a large number, in front of the formula, it means you've got multiples of the element or compound. So for example, if I put a big 2, the coefficient 2, in front of H2O, which we know is water, it means that you literally have 2 water molecules. So you can see there in the diagram there that you have 2 water molecules. So you've got, although you've got 4 hydrogen atoms all together, so you can see 2 times 2 is 4, 1, 2, 3, 4, and that you've got 2 oxygen atoms. They exist in separate molecules. That coefficient affects everything within that formula. So it doesn't just affect the hydrogen, it affects the oxygen as well. But because that hydrogen's got a 2 after it, it's 2 times 2 is 4, and 2 times 1, because you haven't got a number after oxygen, is 2. So you can see you've got 4 hydrogens, you've got 2 oxygens split between 2 different molecules. And like I said, the coefficient at the beginning tells you how many of that molecule you have. Now, what I would like you to do is I'd like you to take some time out. I would like you to actually pause the video to work out the number of atoms for each element in the following compounds. What I mean by that is if we take this example, 3MgO, because we've got the coefficient 3 at the beginning, it means we've got 3 magnesiums. Because we've got a coefficient of 3 at the beginning as well, it means we also have 3 oxygens. Remember, the coefficient multiplies everything within the formula. So what I would like you to do, I would like you to have a go at each one of these formulae. Okay, you've got formulae there. I'd like you to pause the video and take some time out to have a go at these. Remember, the subscript number only refers to the element that it follows. So if you take some time out to actually have a go at these, and then when you're ready to resume, okay, then press play. Right, okay, I hope you took some time out to attempt these questions. So for example now, if we go through the answers now, you can check your work, green pen mark your work. So if we take this example here, you can see that you have 2 hydrogens because that's subscript 2. You only have 1 carbon because you haven't got a subscript number that follows it. Neither do you also don't have a coefficient. And again, you've got 3 oxygens. This one here, your hydrogen peroxide, you can see you've got 2 hydrogens, you've got 2 oxygens. This one's a little bit more complicated. You can see that you've got 6 carbons, but look, you've got 2 hydrogens here. But because you've got a hydrogen here within the brackets with a 4 outside, that means that you've got 4 here, you've got 2 here, which is 6 in total. You've got 6 hydrogens. And then you have 4 oxygens because of 4 outside those brackets. Now this one's a lot more complicated. You can see you've got coefficient here, you've got subscript numbers, and you've also got brackets. And to make it even harder, there's also a subscript number within the bracket. Now this subscript 3 means that everything within the brackets is multiplied by 3. But this subscript 4 within the brackets only applies to oxygen. This subscript 2 applies to magnesium. And then the 2 multiplies everything within the formula. So if we look at this example here, if you've got magnesium with subscript 2, that means you've got 2 magnesiums. But because you've got the coefficient 2, 2 times 2 is 4. If you take phosphorus here, because phosphorus has got a 3 outside those brackets, that means that you have 3 phosphorus. But if you then multiply that by 2, the coefficient, then that means you've got 6 phosphorus. And then oxygen, because you've got a 4 on the oxygen, okay, the subscript 4, that means there are 4 oxygens within that bracket. But because you multiply it by 3, 3 times 4 is 12, and then you multiply by 2 because of the coefficient. That gives you 24 in total. Then what you have here, okay, at the bottom here is slightly simpler than the one above, but very, very similar. Here, because you've got the coefficient 3, it means you've got 3 magnesiums. Because you've got 2 outside the brackets, that means you have 2 nitrogens. But because of the 3 at the beginning, the coefficient, 2 times 3 is 6. Oxygen is a lot more because oxygen, you can see there's 3 inside the brackets, 2 outside. So 2 times 3 is 6. 6 multiplied by that coefficient is 18. 3 times 6 is 18. Now, hopefully, you got 100%. But if you didn't, what I'd like you to do is make sure you go over this again. Listen to the feedback when I go through the green pen marking. So we've got a checkpoint here. If you know the ions, you can work out the formulae of these compounds. Now, I've been quite kind here in that I've given you the ions. Under normal circumstances, I would expect you to have revised these and know these off by heart, so you could actually fill in this column yourself and then use that to go on and form the chemical formulae. So for example, if we take this one here, calcium, calcium's in group 2, so it forms a 2+ ion. Carbonate ions that we would have to revise as CO3 2-, 2 negative charge. So what would be the chemical formulae of calcium carbonate? Well, the ions have to cancel each other out in terms of charge. So if I have 2 positive here and 2 negative here, they directly cancel each other out. So you would have one of these ions and one of these ions to give you calcium carbonate. That would be your chemical formulae. Sodium hydroxide, well, sodium's in group 1, so it's a 1+ ion. Hydroxide ions are OH-. Again, the charges are equal but opposite. For that reason, both of these ions come together within that formula in a 1-to-1 ratio. Lithium chloride, again the same thing. You have 1 lithium because it's in group 1, 1+. Chloride is in group 7, 1-. When the lithium and chloride come together, okay, you make lithium chloride with 1 lithium, 1 chloride ion. If we look at silver oxide and we take silver to be Ag1+, you can see the single plus there, and you can see the oxide, which is your oxygen ion, is O2-. We can see that these charges don't balance. You would need an additional silver in order to balance the -2 on that oxygen. That means this is where you would use a subscript letter, because you would have 2 silver ions for each oxygen ion. So Ag2O. You have a similar example here, but this time it's the calcium, the metal ion, where the charge is greater. So you can see that calcium there is Ca2+, and hydroxide is OH-. So you actually need a second hydroxide ion, the OH-, to cancel out the calcium ion. And that gives you Ca, open brackets, OH, close brackets 2. You need to put brackets in, because if you didn't and you just put the subscript 2, it would only apply to the hydrogen and not to the oxygen as well. And you can see that there, that molecular ion is composed of the oxygen and the hydrogen. You need 2 oxygens as well as 2 hydrogens. So make sure you put brackets in there. Now, what I would like you to do now is I'd like you to pause your video. And I'd like you to have a go at doing those on your own before you look at the answers. Again, it's a very, very similar exercise. If the charges don't balance, how many more of each type of ion would you need for them to balance? Remember, they've got to be equal and opposite. And then once you know which ions are involved and how many of each type of ion, then write out the chemical formulae. This is really good practice before you go on to do balancing equations. Right, so pause your video now. Take some time out to do that on your own. Right, okay, I'm hoping you did that on your own, okay, and you've resumed the video now. So for the first one, you should have had AgBr for silver bromide. That should have been your answer for magnesium oxide. Copper chloride, you can see that you need an additional hydroxide ion to cancel out the 2 positive on the calcium ion. So again, you would have seen calcium, that should have been copper hydroxide. That A should be a U, and that A should be a U as well, okay? So just that, okay? That should be a U, that should be a U. Ca is calcium, Cu is copper. That's a typo there. That's copper, Cu2+. So copper 2 oxide, you can see that copper 2+, okay, oxygen is 2-. So those will balance out. I'm just going to adjust that for you. So I'm going to annotate that now. So that should have been, okay, here, that should have been Cu2+, okay. Obviously, I can't make that when I annotate it superscript up here, okay. I'm just going to scribble out that one now, okay. So that one there should go, okay, that's gone, okay. Over here, that should have been Cu. Just make sure that you do that on your own. Okay, so I'm just going to clear my scribbles there. So if we look at this example here, silver nitrate, again, 1:1. So silver nitrate would look like this. You can see calcium sulfate would look like this. You see sodium sulfate. Now here, 1+, 2-, for which reason you need an additional sodium, and therefore you can see 2 sodiums. You need an additional sodium here, and that would be sodium sulfate. Okay, so I hope you included 2 sodiums. I'm going to draw that in there as well for you, so just in case you forget. So you would need an additional sodium here as well. Okay, so to cancel out those 2 negative charges. And then finally, zinc chloride, because you've got zinc's 2+ and chloride is 1-, you actually need an additional chloride ion to cancel out the 2 positive charges on the zinc, for which reason you would have, oh, that's again an error there. You can see that for that one, you would actually have ZnCl2, okay? And the reason why it's ZnCl2 is because you have 1 zinc and you have 2 chlorines. Okay, so moving on swiftly. Okay, I'm just going to remove my annotations there. So that brings us on to lesson 2. Now, what I would suggest you do is you take a break, okay, because that's a lot of information. That's a bit of an information overload. What you need to do is have a break. I would say give yourself half an hour to an hour at least before you go on to lesson 2. And within lesson 2, I'm going to be teaching you my method, which is called the tally method, for balancing equations. So go and have a break now, pause your video, or come back and have a look at this video later for lesson 2. Right, lesson 2. Lesson 2 is all about balancing chemical equations using the tally method. Now, here you've got the formulae, okay, for an equation. You can see you've got nitrogen, you've got hydrogen, and you've got ammonia. But you can see this isn't balanced. How would you balance this equation? How would you make sure that you had the same number of atoms of each type of element on both sides of the equation, on the side where you have the reactants and the side where you have the products? Well, this is my method, and to be honest with you, it takes a bit longer to do it this way, but it ensures that you don't make a mistake. It means that everything's clear in front of you and you're much less likely to make an error. And in exams where your mind's clouded, you've got the pressure on you, you're beginning to forget things because you're under pressure. Sometimes it's good to do a method where you've got everything written down in front of you. So therefore, you're not going to make a silly mistake. And that's where this tally method can be really helpful. So what do you do if you get given a question like this where you have to balance an equation? Well, the first thing is you've got to establish that this side is your reactants and this side is your products. This actual reaction here is actually a reversible reaction. When we look at the tutorial on the Haber process, we'll go into that in a bit more detail. But just for the sake of this particular tutorial, let's call nitrogen and hydrogen your reactants, and we call ammonia here your product. Now, the next thing you do is you draw a line straight through that arrow, separating the reactants from the products. So there's no confusion there. And then what you do is you then do a tally of the number of each type of atom on both sides of the equation. So if we look at this side of the equation, the reactants, you've got 2 nitrogens and you've got 2 hydrogens. Now, because you've got conservation of mass and atoms aren't gained and atoms aren't lost, the products should actually have the same number of each type of atom. So if you look at ammonia over there, you can see that ammonia only has 1 nitrogen, but it has 3 hydrogens. So we can see that is definitely not balanced. So that's where we have to go about balancing it. So there must always be, as I said, the same number of each type of atom on both sides of the equation. And this is where we add coefficients, the big numbers at the beginning, to multiply the elements and the compounds. You can never add a subscript letter. So do you remember beforehand we talked about water and hydrogen peroxide? If you added an extra subscript 2 to water, H2O, to become H2O2, water would become hydrogen peroxide, which is hair bleach, okay? That's very, very toxic, very poisonous. You wouldn't drink that. So never add subscript letters. You can only add coefficients, okay? And obviously the coefficient multiplies everything in the formula. That's why it was so important to learn about formulas in the earlier part of this tutorial. So what do we do? Right, well, I'm just going to add a point here as well. Can you see that nitrogen I've included first and then hydrogen second? I've done the same here and here. That's to make sure it's really clear when I'm looking at my tally that I'm looking at nitrogen on the top line and hydrogen on the second line. Again, that stops you getting confused in the exam. If you line them up, so nitrogen, hydrogen, nitrogen, hydrogen, they're always next to each other on the same line. It stops you getting confused over what atom of what element you're dealing with at that particular time. So if we look at this here, then we've got 2 nitrogens, we've got 2 hydrogens, we've got 1 nitrogen, 1 and 3 hydrogens. How are we going to make this balanced? Well, what you could do is you could balance a number of nitrogens, and how you could do that is you could put a coefficient 2 in front of ammonia. That means you now have 2 nitrogens. But because it's a coefficient, it affects a hydrogen as well. So that 3 becomes multiplied by 2, because you've got 3 hydrogens there, to form 6. So you now have 2 nitrogens and you have 6 hydrogens. They're your new numbers. So that's fine, your number of nitrogens balance, but now you've got to balance your number of hydrogens. How are you going to make 2 become 6? Well, you can multiply by 3. 2 times 3 equals 6. So now you have 6 hydrogens on your reactant side. So now you can see 2 nitrogens, 6 hydrogens, 2 nitrogens, 6 hydrogens. Your equation is now balanced. Okay? Right. Let's try and move on to one that's slightly more difficult now. So let's look at this example here. This is example 2. So they're your reactants, they're your products. Draw your line through the arrow to separate the reactants from the products. And then you go about doing your tally. So you can see that you have 1 sodium, you've got 1 fluorine, but you've got 2 bromines. Do the same for the other side, but remember to do it in the same order: sodium, fluorine, bromine, okay? So sodium, you have 1. Bromine and fluorine are still to go, but remember to write fluorine next so they match up on the same line. Fluorine, you've got 2, and bromine, you've got 1. And then what you do, okay, is you try and work out what coefficients you would actually require to ensure that the numbers on both sides of the equation, reactants and products, are balanced. So you don't have to do anything with sodium because at the moment, sodium is balanced. But fluorine isn't balanced and neither is bromine. It doesn't really matter which one you start with, whether or not you start to balance fluorine or bromine. But with my example, I've tried to balance bromine first. Now, If you want two bromines like you've got on this side, then you would put the coefficient 2 in front of sodium bromide. You now have two sodiums because that coefficient affects sodium 2, and you have two bromines. Your bromine, okay, are balanced, but now you've created an extra issue. You've now got two sodiums on this side, you've only got one on this side. So what you need to do is you need to balance not only the fluorine, but the sodium as well. And to turn both of sodium and fluorine into 2, okay, you would place a 2 in front of sodium fluoride. So now you have 2 fluorine, you have 2 sodium as well, okay, and that equation is now balanced. So you would have 2 of those there as well. Don't know why I didn't put that 2 there. You'd have 2 sodiums, you would have 2 fluorines. Okay, so that is now your balanced equation. So moving on to another example, okay, again, they get increasingly difficult. So I'm just going to remove my annotation there so it doesn't affect my next slide. You can see this one, example 3, is slightly more difficult. So what you can see there is you've got lead and you've got hydroxide, okay, ions there. You've got a 2 outside those brackets, which would apply to the hydroxide. You've got HCl, you've got H2O, and again, you've got lead chloride here. So again, you do the same thing, reactants and products separated by an arrow. Separate the arrow with a line. And then you can see that you've got your reactants and products separated. You then go about doing your tally. So you can see on this side that you have 1 lead atom, but you have 2 oxygens because of that subscript 2 outside the brackets. And you have 3 hydrogens. And the reason why you have 3 hydrogens is because you have 2 times 1 here, which is 2, but you have that additional hydrogen there, which gives you 3. And then you have 1 chlorine over here. Now again, you would write down on this other side in exactly the same order: lead, oxygen, hydrogen, chlorine. So same order: lead, oxygen, hydrogen, chlorine. And you can see on this side that you have 1 lead, you only have 1 oxygen, you have 2 hydrogens here, and you have 2 chlorines here. So you can see that this again is not a balanced equation, so you've got to go about balancing it using your coefficients. Again, to make sure you've got the same number of types of atom on both sides of the equation. So you can add a coefficient to multiply. So if we put a 2 in front of HCl there, okay, we can see now that we have 2 chlorines, okay, but we now have 4 hydrogens. And the reason why we have 4 hydrogens is because 2 times 1 is 2, but you've also got 2 times 1 here as well because that 2 outside the brackets. So 2 plus 2 is 4. If you put a 2 in front of water molecule here, so you can see that that water molecule's now got a 2 in front of it, you can see now that 2 times 2 is now 4, okay, hydrogens, but 2 times 1 means that you've got 2 oxygens here. So now you can see you've got 2 oxygens because 2 times that 1 oxygen, but 2 times 2 is 4, so 4 hydrogens. Now, if we look at our equation so far, then we've got 1 lead, we've got 1 lead. We've got 2 oxygens on this side, we've got 2 oxygens on this side. We've got 4 hydrogens on this side, we've got 4 hydrogens on this side. We've got 2 chlorine on this side, we've got 2 chlorine on this side, which means that our equation is now balanced. This one, again, is more difficult. So again, you've got your reactants, you've got your products. Now, again, you draw your line through the arrow to separate the reactants from the products. Now, I'm going to point something out to you now. Never, ever try to start balancing an equation by using an element that appears in more than one formula on the same side of the equation. So in this, what does that mean? Well, this answer here, can you see that oxygen appears in sodium hydroxide? but it also is over here in potassium phosphate. For that reason, definitely do not start with oxygen because it's in more than one, okay, formula on the same side. Coincidentally, it's also in more than one formula on this side as well, but it wouldn't have to be. If you see that any element appears in more than one compound on the same side, then leave that to last. By the time you've balanced it, it usually sorts itself out, okay? That would make it very difficult if you try to balance oxygen first. So again, you do your tally. So you've got 3 sodiums, you've got 1 phosphorus, you've got 5 oxygens, so you've got 4 here, and you've got 1 here, that's 5. Okay, you've got 1 potassium there, and you've got 1 hydrogen. What you do then is you do exactly the same for the product side. So again, make sure they're in the same order so you don't get confused. So you've got 1 sodium on this side. You have 1 phosphorus on this side. You have 5 oxygens because you've got a subscript 4 next to that oxygen, which would suggest you have 4, and then you have an additional oxygen there, which you have is 5. You have 3 potassiums here. You have 1 hydrogen. Now you can see that those numbers do not match, therefore that equation is not balanced. So what you now do, as I said, is you go about adding coefficients to balance, but do not start with oxygen for the reason I mentioned before. So again, I've just put a point there, leave oxygen to last because it appears in more than one formula on the same side of the equation, actually on both sides, which means doubly don't start with that one, okay? So what I started with was with sodium. So if I put coefficient 3 in front of sodium hydroxide, I now have 3 sodiums. But that has now affected my oxygen. And again, that's why you don't do oxygen first, because whenever you add a coefficient to any of these, it's going to affect oxygen too. So you've got 3 oxygens here now and 4 here, which means that you now have 7 oxygens. But because you've got that 3 there and you've got hydrogen there, that means you've now got 3 hydrogens as well. Right, so the next one that I went to balance was potassium. So because I had 3 potassiums on this side, ideally I want 3 potassiums on this side. If I put 3 in front of potassium hydroxide here, I've now got 3 potassiums. But again, I've affected the oxygen and the hydrogen with that coefficient. So 3 times 1 is 3 oxygens, plus the additional 4 oxygens there, means that I have 7 oxygens altogether on my reactant side. And the same thing for hydrogen. If I put a 3 coefficient, that 3 affects that hydrogen. I now have 3 hydrogens. Now if we look at our equation here, 3 sodiums, 1 phosphorus, 1 phosphorus, 7 oxygens, 7 oxygens, 3 potassiums, 3 potassiums, 3 hydrogens, 3 hydrogens. We can see now that that equation is balanced. Now, what I would like you to do is I'd like you to try and balance these chemical equations. There's quite a lot for you to do. You've got some there and you've got some more there. If you can balance all of those equations, then you will find balancing equations very easy in the exam. Now, I'm not going to provide the answers today. I'm actually going to do another tutorial to follow this one up where I provide the answers, because I really would like you to have a go at these. So have a go at them. Don't worry if you can't do them. Another tutorial will run to provide you with the answers and the feedback for these. But if you get stuck, go back over my 4 examples. Make sure you go over them, practice the example ones again to ensure that you're very clear, and then reattempt these practice ones. And again, the answers to my last 2 slides will be posted in my next tutorial. Okay, thanks for listening. Take care. Bye-bye.